Good morning, mathematicians. I suspect you all had a productive week, improved lots of theorems. Now, it's time for, proving more theorems, because it's the weekend. For me, it's time to grade a lot of papers. Good morning, Edit Smith. Oh, come on, why is this? There we go. Okay, where should we start today? I like starting in Reddit. Maybe there'll be something fun there. How critical is information retrieval? Oh yeah, I was looking at this post last night. They were talking about a couple different scenarios. Case one, you solve a problem, but you're unaware that is already known in some other niche field and has been for 50-ish years. Case two, you get stuck for some time, but you don't get unstuck because even though you searched, you couldn't find an existing solution because it may not have been worthy of its own paper, even if it's standard sleight of hand to some. And three, oops, your entire paper is basically the same thing as someone else just published less than 2 years ago, but recent enough and it feels distant enough to you that you have no way of keeping track of recent developments therein. Well, I think all of these things happen. And I guess it sucks in a certain sense, but am I financially free? Absolutely not. Not even close. Yearly, I make less than someone working full-time minimum wage in my city. So, yeah, very far from it. Grad schools aren't paying a lot these days. But, yeah. I don't think case 3 happens so much these days. Just because it's pretty easy to, like, it could. It's not inconceivable, but the thing is, like, even if something's in a very different field, like, there's a chance that you'll find it if you're looking at things online. And also, a lot of fields are, like, a lot of fields are pretty deep at this point, and so to make a pretty new novel thing in one field, like, it would have to be an adjacent field, you know what I mean? The field wouldn't be far away enough, typically. I mean, it can happen. There's this one hilarious case. It's a famous case. There was a paper in the 90s, I think it was. I don't remember what it was. It was like a biology paper or something. And they basically reinvented the trapezoid rule from calculus. So it can happen, but also, like, yeah, reinventing the trapezoid. Hi, Jens. Reinventing the trapezoid rule from calculus as a biologist is not quite the same as a mathematician, reproving something that was just proven like 2 years ago or something. But yeah, I don't know, it can happen. There's also some papers that just don't get a lot of attention. Maybe they get missed, or there's some result in there that gets missed, and that could be for a whole whack of reasons, right? Maybe the person who published the paper didn't advertise it a lot, or give a lot of talks, or maybe it wasn't so clear from the paper that what they were doing in the introduction and whatnot. I think case 2 happens a lot. I don't know. I'm struggling with my own things. Certain things I'm working on where it's like a lot of people just seem to claim that some such thing is true, but then it's like, well, there's actually a lot of details that seem to be missing to claim that that thing is true. And it's like, yeah, I can believe that somehow on aggregate, the references you need to stitch together to complete the proof are known to the experts, but it seems like a little much to say such results are known. But yeah, I don't know. This is an interesting question. Do you have a comfort proof? Construction of the Vitali set and the subsequent proof of non-existence of measurable sets is, yeah. I don't know. I don't know what I'd consider a comfort proof. Reading history of model theory. Oh, that's interesting. Yeah. Is there like a, well, probably isn't, the longer, the more detailed and better it will be, but I'm wondering if there's a short overview of the history of model theory. I don't know if I have a comfort proof. I'm trying to think. I mean, there are proofs that I like. I was talking about, a couple of weeks back, the proof that the fundamental group of a topological group is abelian. That's a nice one. Not particularly deep or famous. R3 is the union of a disjoint collection of unit circles. Wow. Yeah, that's hard to think about. Hodges? Short history of model theory? No way that's the same Hodge from, like, geometry, right? Oh, Hodges, right. I see. Yeah, not Hodge. Okay. Nice. Yeah. Oh, I'll have to go. I guess I'll have to sign in to the library to get it, maybe. Oh, no, maybe I can just click on it here. Yeah, I guess I'll have to. Yeah, maybe I'll take a look at that later. Or is there a rough draft here? What? Does this look like it's the same one? Well, anyways. Oh, what's this? Oh, yeah. Fixed point theorem. I need to better understand the fixed point theorem perspective, because I know it can get used pretty generally. Okay, I should probably yap about something, right? I should probably yap about something until questions start pouring in. Oh, different version of the same article. Awesome. Okay, great. I'll just read that then. Yeah. Yeah. Okay. What should I yap about? I mean, yesterday we did some computations with perverse sheaves, so that's always fun. You know, when I started these office hours, I was also imagining that there would be more like, well, I guess it's on me because I just started yapping about these things, but you know, maybe there'd be more lower level like undergrad questions. What are colimits? Why are colimits seen less often than limits outside of category theory? I don't know if that's true. I don't know if that's true because I mean, well, first I always get my left and right confused. My co-limit and my limit. At least in intralinear algebra, we see kernels but no co-kernels, for instance. Yeah, okay. I mean that makes sense, but I mean for example, like products are limits, right? Products are limits. Co-products are co-limits, right? Both of these things in like basic set theory, right? So in sets, products are Cartesian products. Co-products are disjoint unions of sets, right? Products of topological spaces, or let me say products of groups. So products of abelian groups, let me say, are both products and coproducts. Is it just that limits are better behaved? Then I assume one of those you meant colimits. Direct product of groups is much nicer than free product. Yeah. I don't know if they're. I don't know if it's actually better behaved, right? Like I think you're definitely right. Like the free product is maybe more complicated, but like as a general principle, right? The limit versus a co-limit shouldn't be any better or worse behaved, right? Like you're just drawing you're drawing a triangle like this, or you're drawing a triangle in the other way, right? For the sort of defining universal property of a colimit. Limit versus colimit, right? So strictly speaking, from a category theory perspective, one really isn't behaved better than the other. Co-limits might be less common in undergrad education, but they're just as common as limits in doing actual math. Yeah, that's true. I would agree. And in some sense, it's almost a little weird why co-limits don't show up as much. Like I think we could be talking about the co-kernel just as much in undergrad math, right? So like often one place where people encounter kernels, maybe even in their first year, maybe second year, is the linear transformation, right? And we talk about the kernel. The kernel is well, you know, the kernel being 0 is equivalent to t being injective, right? And so the dimension of the kernel is somehow a measurement of how far away from being injective your map is. Whereas meanwhile, the co-kernel of your map, this is going to just be W modulo the image of t. And so in the same way, this will be 0 if and only if your linear transformation is surjective, right? And honestly, this isn't like this is not really harder. I mean, mind you, here's maybe one thing is maybe if this is a first year linear algebra course, maybe quotients are harder to understand because you're dealing with like equivalence classes and stuff. So I could maybe see the point. I could maybe see that as like that's the one barrier to why we decide not to talk about co-kernels, because maybe like for the engineers and stuff that are just need to understand vector spaces enough to use them, maybe they feel like it's not worth going over like equivalence classes and proving that it's the vector space operations are well defined under them. You once saw the interpretation that a lot of the categories we're familiar with are concrete, but their opposite categories aren't, and concreteness makes them easier to grasp. Makes sense, because for colimits you usually need to create something new, but for limits it's just a sub-object of the existing thing. Yeah, that's true too. Yeah, that's true too, right? Like a limit is usually going to be like some sub-object of a product, and a colimit rather is going to be some quotient of a disjoint union. Like in terms of sets. Forgive me, am I writing the arrow the wrong way? I probably am. But in terms of sets, the limit of some like set family, and so consequently in all sorts of mathematical objects that can be phrased in terms of sets. Normally this is a sub-object of a product, and the co-limit will be a quotient. Will be a quotient of the coproduct. Injective maps are somehow nicer than surjective maps. Maybe. But I'm interested this comment about the interpretation. A lot of categories we're familiar with are concrete. So I wonder specifically what you mean by that, because there's concrete in the sort of colloquial sense. That we can, just give a nice explicit description. But there is also a very technical, precise term of what it means to be a concrete category. So let me come back to this in a second, though. Saw someone say, your channel is great. Can you recommend other similar content? I can recommend a lot of math channels. I don't know similar content necessarily. I feel like I've got my own little niche, at least in terms of doing this these random office hours. Is it possible, can you see channels that other people have subbed to? Like if you go to my channel, can you see the channels that I've subscribed to? Because if you can, I would go there. Subscriptions. Normally it's on the side here, but I guess I need to. Yeah, I don't know how to bring it up, but there is a previous one. There was a previous office hour where I went through a bunch of recommendations of some of my favorite creators. Give me one sec. Subscriptions here. Yeah, so, well, I mean, Sheafification of G is probably my favorite channel right now. My favorite math channel right now. But I would not describe the content necessarily as similar to what I'm doing. Yeah, I guess part of my question to you would be similar in what sense? What kind of what aspect of my content are you looking for? Because I don't think anyone's doing live office hours, but there's obviously lots of great math videos out there. What's another? I mean, math curator Zana-chan, I think her name is. That's one that I was raving about before, trying to convince people to go there. Of course, Aleph Null is awesome. Yeah, yeah. Maybe let me know specifically what more you're looking for, and I can recommend some more stuff. Very broadly similar, but you also love G. Yeah, yeah. You remember you were told that Grothendieck preferred quotients rather than subspaces. Interesting. So, for example, he would define the Grassmannian as a quotient space. Really? Huh. That's very interesting. That's very interesting. I should make like a community poll. Figure out, get people to vote on if they prefer injections or surjections, subobjects or quotients. Yeah. I mean, somehow, yeah. I don't know. I could see the appeal of quotients, right? Because in some sense, like, I guess going back to this idea of like, okay, well, either you're looking at a sub-object of a product or a quotient of a co-product. Like, I guess going back to this idea, well, someone made a comment. They made it in the opposite order of like, oh, well, one takes something that's already there and the other sort of constructs it. But kind of they're like, you could imagine that, well, maybe it's harder to carve out a subspace, right? Because now you need to give some particular list of data that checks if something is in a subspace or not. But somehow maybe the quotient, you already have actually all the objects you're sort of already holding on to. I mean, you can make the same argument. Oh, then it's harder. You need to check if two things are equivalent or not. But you can always just take any of the objects that originally were in your set already are determining something in the equivalence class, as opposed to you might not know if they determine the same thing or not, but you know they determine something. Whereas in the limit, it's maybe more mysterious if you grab an arbitrary element here and then try and ask yourself if it belongs to the sub-object or not. So that's me steelmanning quotients, I guess. Interesting. In the case of Grassmannians, it's important for moduli stuff. Because you want to parameterize quotients of a locally free sheaf, which may not be subsheaves of it. I'm not sure I understand that comment, but I believe you. By the way, matrix coefficient, if you, I don't know if you had a chance to watch my ramblings about the perverse sheaf calculations yesterday, but I hope if you did, they were useful, and feel free to ask any questions about it if anything was unclear. I also have a somewhat random. Oh, let me go back. I just want to read the definition of concrete category, because I'm not sure if the comment from Ethan was about the colloquial sense of concrete or literal concrete. In mathematics, a concrete category is a category that is equipped with a faithful functor to the category of sets. Okay, I mean that is I would say in general that is true that most of our categories are concrete in that sense, and then certainly, certainly, if you take the opposite, I would not expect that to be a concrete category. So it makes sense under this interpretation, actually. This functor makes it possible to think of objects of the category as sets with additional structure. Right, yes. And that's absolutely true. That's absolutely true. On the other hand, the homotopy category of topological spaces is not concretizable. That makes sense. Yeah. And let me just, what was that comment in reference to? The interpretation, a lot of categories we're familiar with are concrete, but their opposites aren't concrete. So I'm not sure I understand then how that wraps up with limits and co-limits, but I could believe that somehow that's in there. Didn't have a chance to get to it yet, but she'll get on it. Okay, cool. Just let me know when and if you have questions. On a separate note, getting comfortable with Satake. So that's great. Awesome. Well, then maybe you can make a video sometime soon to better explain it to me. Yeah, because I have a very superficial understanding of the geometric Satake, and yeah, I mean, probably today, if I wanted, I could sit down and probably get more comfortable with it. But there's always other work to be done, isn't there? It'd probably be a good investment of my time, but yeah, I think I'm gonna put like pretty much all work aside this weekend and just grade. Very painful weekend for me. Pray for me, everyone. I'm not religious, but pray for me nonetheless. Pray to Gretel. Speaking of, I was thinking to beef up my channel, maybe I could start maybe I should be starting random math beefs with people on YouTube, because people were on a Facebook page I saw was talking about this guy who was so this guy had a video. You can see I watched half of it. City tutoring math. So this guy's really interesting. I thought of it because I mentioned praying, and this guy's like he's kind of interesting. He's super religious, and it seems like he has a very like Platonist view of mathematics, and it's very like wrapped up in religiosity for him, which actually I think is interesting. Here's a total side note. Like, to me, it actually kind of makes sense from a religious perspective to it makes sense from a religious perspective to study mathematics, right? Because if you do think that the universe was created by some creator for humans and life, and if you wanted to know that creator and like understand them and their works, I mean, it does seem like mathematics is a really great way to do that. And so I think there is a really good religious argument for studying mathematics. Anyways, he's kind of an interesting character. I don't like listening to him at all. I find him hard to listen to, which is why I only made it as far in this video as I did. But you know, he starts putting the math sorcerer on blast. Well, yeah, look, he's shaking the book and whatnot. Yeah, he's not wrong. He's not wrong about the things that he says about math Math Sorcerer. So I don't know. Maybe, yeah. I mean, I guess Eric's here for it. Looks like Jens is here for it too. So maybe, maybe I should start making clickbaity videos and start going after the Math Sorcerer and city tutoring math. And what's this other guy? Dimensional algebra. I mean, those two guys, at least Math Sorcerer and city tutoring math, at least those guys probably know some actual math. But this guy, yeah, this guy is just, yeah, he's got total nonsense. He's kind of a crackpot, and people have tried to explain to him why he's wrong in the comment section. It's such a shame that this guy is a crackpot. Obviously I'm not talking about 3 blue 1 brown. I'm talking about the dimensional analysis or dimensional algebra guy, because he's definitely creative, and he definitely has like some understanding of logic and manipulating of symbols. So like this guy probably could have been a creative mathematician, but and he makes nice looking videos, but yeah, unfortunately he chose to be a crackpot. I mean, I guess it's working out for him. This guy's getting way more views than I am, so yeah, I don't know. I do think my backup plan is kind of to just go hard on the grift and just use my knowledge of mathematics to like sell crystals in a really convincing way or something. The Catholic Church has a very interesting history with Euclidean geometry and natural science. Interesting. Yeah, I mean, that makes sense. You were talking to someone about math and Jesus and stuff like that, and the guy said to me, how can someone so smart yet so naive believe in Jesus? I didn't even know what to say. Yeah. Well, actually, so there's an interesting thing to say about those comments. Casual math content is too basic or too crackpot. Well, hopefully I'm filling that void then. Hopefully I'm filling that void. I mean, I was saying earlier that I had hoped maybe my office hours would attract some more basic math questions and rack up views, but this is the way it's been going is the more fun way anyways, to talk about like crazy, whatever, perverse sheaf computations or whatever. So yeah, hopefully, but I also have my fringe rantings about the Moore graph problem, so hopefully I'm just barely staying in the rails of crackpot and not too basic. But yeah, just about this comment with people think that it's funny when people make comments about if mathematicians being smart, like how can you be so smart and do this? And it's like, the thing is, like, being good at math is a particular kind of intelligence, and it just doesn't always translate into being able to effectively interact with the real world. Like, you would think logic is logic, but it's not true, right? Math is kind of, especially pure math, is in many cases divorced from reality. And so honing in on the skills to get really good at the logic inherent in pure mathematics does not necessarily translate into any sort of real world skill. And when I say real world skill, of course I don't mean I could like fix my bathroom door if the hinges are squeaky or something. I just literally mean like existing in the world and, like, I don't know, figuring out how to like make yourself breakfast. Like, there are people in this world or like just socially inept or whatever, or just like couldn't cook themselves an egg to save their life, but like they're like, award-winning annals publishing mathematicians. But for the most part, no. I mean, for the most part, it is the case that like people are generally intelligent, and then okay, whatever beliefs you have on top of the world are, I don't know, orthogonal to that. Yeah, there's very religious mathematicians who are successful, and mathematics is a religion, right? Okay, we all just believe that ZFC is consistent. Why? There's no reason to. Well, because we haven't found an inconsistency yet. So yeah, sure. But we provably won't ever be able to prove that it's consistent unless we assume something stronger. So, yeah. What was the other thing I was going to bring up? I was talking about this article. Speaking of philosophy. What's... maybe if I just type this. No, do I have it in here? Oh yeah, here we go. Structural invariance and univalence. This is a really cool sort of almost philosophy of math paper. The geometry of the natural world, after all, not being Euclidean and corresponding to developments in mathematical logic, have a devastating impact on philosophy in general. Did it? I mean, what do you mean by devastating? Because I don't know. If anything, I think it improved philosophy. I mean, it might have been shattering of some worldviews at the time, but would it be a devastating? I don't know if that's just a particular choice of wording I would have used, but recent development of an interpretation. Yeah, so anyways, what's the point of this article? So he sort of gives an argument for why ultimately something like homotopy type theory is actually sort of philosophically a better foundation for mathematics. And the idea is this, is that we sort of all, like most mathematicians, kind of implicitly believe that isomorphic objects are identical. So this is the principle of structuralism, as he calls it. But the problem is that in set theory, these two, so this sort of identity principle, A is identical to B if A and B have all of the same properties. It doesn't really work out because equality is too. Sorry, that's not true. It does work. It does work out because equality is very strict, right? So and we encode, like, one of the properties is like all elements of A belong to all elements of B and vice versa. But specified certain classical philosophy in particular, the theory. Yeah. I figured. Yeah. I guess in that sense, yeah, what you say is true. Yeah. Yeah, but very often we would like, we want to consider. Hesitant say anything but all of math, but within homotopy and category theory, learning homotopy type theory is so enlightening. Yes, I so agree. It's really a new approach to the notion of equality, and it's beautiful. It is. Yeah. It's so... I don't know. Yeah, it feels like an awakening when you think about things in these different ways. So, okay, let me rant about that in a second. But so I'll just finish selling you on this paper. So, yeah, the thing that he sort of argues is, well, you know, oftentimes we really just care about two objects being isomorphic. Um, and the sort of naive way of course, taking this like this like A is equal to B if and only if A and B have all of the same properties, is if you take this sort of naive thing, which is basically true in set theory, and then you try to replace it with isomorphism instead of equality, then it kind of falls apart, at least if you're staying within a classical framework. But if you if you move over to homotopy type theory framework, then this is very this is sort of very natural from that perspective. But yeah, I mean, okay, I've already made a video, you know, where I talk about some of the basics of type theory and homotopy type theory, but yeah, I should just say that like one of my favorite things is when a couple summers ago we were doing I had a reading group for the hot book with some students, a mix of grad students and undergrads, and the thing that I just loved so much about it. So let me just write out what one of the statements of an isomorphism of what that is. So what is it? It's something like how do I write the what's the homotopy, what's the type theoretic version of and? There's some other way to put it, and I'm blanking right now. There's some other way to put the and here. But the point is, yeah, there's some other way to write why am I... Oh, yeah, it's just the product. Yeah. Right, and that's getting to the point that I want to make, is that there's multiple interpretations of every symbol. So you can read this symbol either as we're taking the product over all x in x, or you can understand that this symbol means the same thing as for all x in x. And then same thing with this symbol, and then, yeah, exactly, it's and. And then same thing with this symbol. You can interpret this either as like a Cartesian product of spaces, or you can interpret it as the and symbol. And sort of the amazing thing about this is that you could prove a statement like this either interpreting this as a statement about geometry, like you could think about this as some product of spaces, and construct your argument geometrically, right? And like write down the steps like formally, like as you would in the proof assistant or something. Or you could also interpret these in terms of logical symbols, like for all x in x, for all y in y, interpret this as an and then again, just sort of symbol push, but symbol push in the way that you would think about it in like your first year logic course or something. And so instead of spaces, you're imagining all of these things as propositions. And the incredible thing is that both ways are totally valid. And in fact, like there were instances where we would discuss a problem and one person would explain the proof. They would explain the steps of the proof using geometry. Like they would explain each step in the language of geometry. And someone else would explain each step of the proof in the language of logic, and yet somehow they both arrived to the like literally the exact same steps of the proof. And this is incredible to me. The flexibility of thinking that it affords, and that both interpretations of these statements can be like successfully realized simultaneously. Yeah, I mean, yeah, it's incredible. Yeah, I don't know what else to say. It's just, it's the feeling, the brain feeling, the brain feel when you when these ideas click is I don't know, it's cool. It's cool. But yeah, so I don't know, maybe in the future I'll try and rewrite all the foundations of Langlands and homotopy type theory. Actually, that would probably be easier if I learned categorical local Langlands, because that's already ripe. That's already been cast in categorical language, so that's probably a lot easier to make sense of in homotopy type theory than the classical approach to Langlands. You know. Anyways, I guess I might leave it there. Yeah, I guess it's time to grade stuff. Maybe go for a run. Could I clarify which logic and geometry we're considering here? Yeah, I just mean well, logic, I mean just like ordinary like propositional logic, right? Like this statement, I mean it doesn't the statement doesn't look very different in basically like the propositional logic. Like, okay, I'm really gonna abuse terminology here, and I'm gonna pretend these are sets, which is like kind of a no-no, because actually these are types. But like the statement just becomes the extremely similar looking thing. And I just mean you could like argue through this. You could sort of manipulate this statement according to just ordinary rules of propositional logic, where say you're treating all of these things as sets, and you're treating these as universal quantifiers, and this is the AND operation. The geometry that's going on is I mean, it's not, so I should say it's not literal geometry, but well, it is and it isn't. I mean kind of the thing that homotopy type theory does, it's in a sense it's kind of like a synthetic approach to homotopy theory, in a certain sense. So these things, like the spaces that we work with, instead of sets, we work with types, right? And okay, there's type theory underlying this. You can think of it very similarly in the way that you think about like sets, for the most part, for the basic type theory thing. So I mean, even a set, you probably conceive it as some sort of geometric, not strictly geometric, but some sort of collection of points, right? But then, okay, when we bake the univalence axiom into this, okay, maybe this is kind of going to be a crazy thing, but we should basically think of our spaces as infinity, our types as infinity groupoids, right? And so, I mean, the classic example of an infinity groupoid is if you take a topological space and you take its fundamental groupoid, right? So that's the category where the objects are given by the points. So points are objects, and your homotopy, your homs between 2 points are just paths. Paths from x to y. And what are your morphisms between paths? Well, those are just homotopies. And those are your, 2 morphisms. Your 3 morphisms are homotopies between homotopies. Your 4 morphisms are between that, and so on and so forth forever, right? So that's your fundamental thing about like an infinity groupoid. And so somehow like once we insert the univalence axiom, we're basically thinking about things as our types as infinity groupoids, right? Because like you have some type, let's call it A, and you can have 2 terms of that type, right? And then you can ask, well, are A and B equal in terms of A with respect to the type A? And well, that means A and B. So this is not just a binary thing, right? This itself in type theory, everything, including logical statements, is a type. So this type can be inhabited possibly by multiple objects, right? So this is true. This statement A is equal to B if and only if this type is inhabited, but it can be inhabited by multiple things. So in the same way that there's like multiple proofs of one statement, or there may be multiple isomorphisms between 2 things, or there may be multiple homotopies between 2 paths, this can have 2 things. But then you can ask if X, so then it makes sense to ask if X and Y are equal within the type of equalities. But then again, what is this? This is a type, and it can be inhabited. And you can go ahead and ask again, are alpha and beta equal in the type of equalities and so on. And so we like conceptualize these things like this in the exact same way that you conceptualize like paths and homotopies as like higher morphisms. Okay, that may not have made a lot of sense if you haven't been exposed to these ideas before, but so I'm sorry if that's too crazy of an explanation, but okay, that's the like basic idea, and it might just take some time to go like read up on these things more to digest and process. But that's the rough idea. So yeah, in some sense, like it's not a literal geometry in the way that you're like normally thinking of like, oh, I've defined a manifold or something, but the sort of axiomatic approach of like type theory plus the univalence axiom means that like, yeah, it kind of it's like a foundation of mathematics, but it's a foundation of mathematics that basically axiomatizes homotopy theory. And so the basic objects being types, you can simultaneously you can think of this just as like foundational objects for a theory of mathematics, but you could also simultaneously just conceptualize it as like a synthetic homotopy theory. But you can do these like simultaneously. You can it's like equiconsistent to imagine these things. Yeah. That was a lot. You said you have other videos talking about this? Yes. So I have a video called Hot Boy Summer. The first like 15 minutes is just me yapping about roaming around Italy, but I think I put timestamps in it. And you can jump ahead to those timestamps where I explain a little bit slower some of the details about type theory, the univalence axiom, and then I do some proofs in a proof assistant with these things. So yeah, go check out my video Hot Boy Summer, and maybe I'll make more videos about this in the future. I don't know. Okay, but I'm gonna leave for real now because my coffee's done, and I need to go for a jog, clear my head, mark some papers. Go mark all the papers that you guys have to mark too.